Good news, everyone. NASA has announced the winners of their Phase 1 NASA Innovative Advanced Concept Awards, the NIAC Awards. And this is a collection of really cool mission concepts, science experiments, really sci-fi technology that I try to highlight every year. As soon as NASA presents the winners, I will try to get every one of the people to do an interview with me. And people have been responding and the calendar is filling up, and I am now queuing up all of the interviews that I can get my hands on. And usually I'll get through a pretty big chunk of them. So first up, I've got an interview with Jeff Nosanov. He is the founder of Orbital Velocity LLC. And Jeff's NIAC proposal is called OBLIVION. And of course, that is a backronym that stands for the Observing Black Hole Light via Intensity Correlation. And this is an interferometer at enormous scale where you have two arms of the interferometer, two 300-meter telescopes that are orbiting about 15 million kilometers apart from each other. And they are using a very specific, obscure technique called the Hanbury-Brown twist intensity correlation to measure the brightness of the light coming from the largest black hole in the universe, Ton 618, which is a black hole that probably weighs 40 to 66 billion times the mass of the sun. And with this mission, they hope to be able to see the photon ring around this black hole. So if that sounds interesting to you, enjoy this interview with Jeff Nosanov. Jeff, first, congratulations on winning a NIAC award. You are the first person that I've interviewed in the 2026 batch of NIAC awardees.
I'm honored. Yeah.
Yeah. Well, I mean, I'm glad because this is one of the coolest missions that I've looked at this year's list. And I was really excited. And I was really glad because it's always hit or miss. Like sometimes people just won't get back to me. And I'm like, oh, I really want to know more. Oh, yeah. Yeah.
Well, you know what? I've won. This is my fourth NIAC award. And the previous ones, I didn't have this kind of public engagement in mind, and I should have. So this time I went into it hoping, obviously, that I win, but that I'd be able to tell the story more and get people excited. So I'm thrilled that you reached out to me.
Well, the crazy part is that my audience now is like expecting this, waiting for the NIAC Award season to show up. It's like it's like the World Cup of space news channels. And so, I typically get, 75% of the people who've won them to finally agree to sit down and have a conversation. And then we bundle them all up together into this collection, and that works really well. So, but let's get on to your project. So why don't you give us the title?
Sure. So it is OBLIVION, Observing Black Hole Light. I should really know my own title by heart. But
the backronym.
But basically it's looking at the most distant black hole, at the largest, most distant black hole, 66 billion solar masses, 10 billion light years away, and using that to probe some of the places where secrets to new physics might lie. Basically, the extreme space-time environment in and around an object like that, that's the place to look for the next revolution in physics.
Right. And like, obviously people are familiar with the Event Horizon Telescope, the work that was done to look at M87 and the supermassive black hole at the heart of the Milky Way. And they happen to be sort of the same visual size on the sky. How big or how small is this one? What is this black hole, by the way?
TON 618.
Right. Okay. So Ton 618. Yeah.
It's 20 times smaller on the sky than the other one. It's like a pea on the surface of the moon from the Earth.
But still, that you've got a black hole that, the light has taken 10 billion years to get to us. It is so much farther than Sagittarius star, right?
Yeah.
And yet it is only a 20th the visual size in the sky. This thing is a monster of incomprehensible proportions.
Yes.
Right.
Which is where if the clues are in any of them, that's the place to look. And that's really was one of my initial motivations.
So then what is the plan? What are you hoping to sort of figure out?
Sure. So as the audience, if you're familiar with NIAC, you'll know the phase one study is simulations and modeling, basically answering the question, this looks theoretically possible, is it actually? And what will it take? And that's what we're going to do with this. So we have a estimate, basically a rough estimate of one, that it's theoretically possible, and two, how hard it is. And I'll share that because it's fun. Basically, we can get into how it works later, but the back of the envelope is it would take two detectors that are 300 meters squared, which is pretty big, but they have to be 9 million miles apart. That sounds hard, but that's the easy part. The detection timing has to be accurate to the picosecond
between the two parts of this interferometer.
For each packet of light coming in, you have to measure its time of arrival compared to the others at the picosecond level of precision.
Got it. Yeah.
And that 9 million miles, it's an interferometry approach. And if the distance between the two nodes varies by a meter, 1 meter over 9 million miles, it doesn't work. So that means you have to know its position to 1 meter at some millions of miles from Earth, and you have to control its distance from the other one to less than 1 meter over 9 million miles. So it's definitely a NIAC problem.
Yes, totally. And so it sounds like, I mean, people are familiar with the Event Horizon Telescope, where you've got this worldwide collection of radio telescopes, atomic clock. You're able to record the radio data and then merge it after the fact. Will you be going with the same approach?
Well, sort of. So it's not radio data that we're looking at. We're using an obscure technique developed in the 50s based on something called the Hanbury-Brown and Twiss effect. And it is an intensity interferometry approach. So what we're looking at is basically the flickering of the photons from this thing, and how they bunch up in time over that great distance. And there is a quantum mechanical relationship between the basically that encodes the rough diameter of the source object when viewed from multiple points. So the way I like to explain it is, imagine you're on the West Coast, or you're at California, you're looking at Hawaii, and you want to measure and assume the Earth is flat, and you want to measure the diameter of one of the islands. If there's a couple of lamps on the island that you can see from 2 points in Hawaii, the Hanbury-Brown and Twiss effect shows that if you're looking at both those lamps from different points in California, there's actually the light itself that comes from both of them encodes information about the island, the size of it. And it's a little bit of a rough example because those are two separate light sources. But if it's a star or an enormous source of thermal energy like a black hole, it's a single source where the 2 points, light from 2 points on it, have a relationship that we can untangle into the diameter roughly of the object. And this was used in the 50s to measure the diameter of stars from the ground, which is how I was introduced to it over 15 years ago and became obsessed with it because it's so interesting. Like, why should the universe work that way? But it does.
Right. So then the other sort of piece of this sounds very similar to me to the LISA mission, where you've got these spacecraft that are flying in formation, maintaining their positions perfectly on these 15,000 kilometer arms. So same.
15, it's a similar. Yeah. It's a similar million? Challenge anyway. of maintaining a precise distance between two spacecraft, for different reasons. I mean, they have a laser connection, that's a laser link. That's the core of the measurement system. In our case, likely the laser metrology approach to keep their distance is not the measurement we're going for, but of course it's critical for the data to be of sufficient quality that the interferometric approach can work. But they both have the same ridiculous challenge of maintaining an exact distance.
Right. And at that distance, the problem, of course, is that the amount of time just the light takes to get from one to the other is way beyond your picometer level of measurement. And so there's no way to sort of tune the telescopes in real time.
That's one of the questions is what's the best way to maintain this I'm pretty sure this is the most ridiculous station keeping challenge ever seriously explored, at least that I've ever seen. But it appears to be just barely within the realm of conceivable engineering, which is where NIAC lives, really.
That's right. Yeah, yeah. I've seen people get rejected if they're not thinking big enough, right?
Absolutely. And in fact, I was a reviewer in 2024, and it was a really great experience. But when I left, I thought, you know what? I want to put in something bigger than as big as I can. And the big questions to me that I hope to live long enough to see some progress on are life elsewhere, obviously, but also this why does the universe exist? What's the next leap, from Newton to Einstein to what? Or maybe I should say from Newton to Einstein to Hawking to what, and if I could make a dent in any of that, well, what greater mission could I, set myself to than that?
So right now in your plan, what do you think this mission looks like? Like, imagine you are working on it on the ground. The engineers have put together the spacecraft. Talk me through all the way to deployment and starting to gather data.
Well, as the sort of back of the envelope, is it possible question that we did put together for the proposal, it's basically 2 spacecraft with deployable dishes that maybe launchable together nowadays with something, but really a gentle coast out to the distance. For the proposal, we said, okay, 10 million miles apart, so we'll put them 5 million miles ahead of the Earth, 5 million miles behind the Earth in its orbit. But that doesn't necessarily have to be the architecture. There may also be a reason to use a third one, because with two nodes, you get a one-dimensional measurement. And so part of the study, really the design of any mission, is to evaluate what certain architecture decisions buy you in terms of science. So it may turn out that 6 of them are ideal, but that would cost $9 billion. So point being that it's so part of the phase 1 study is finding that sweet spot in all of the constraints. And of course, I imagine the more spacecraft you have, the exponentially harder the station keeping problem is with all of them. So that will probably hit a limit at some point. But that's the fun of this is trying to find, put the Lego, I always think about it like Legos, put the Lego pieces together in a way that stands up.
Right, right. There was a paper that I reported on a couple of years ago where someone was proposing that you use L4, L5, and L3, and that creates a equilateral triangle that, you do have the Earth's orbit is not a perfect circle, and so you don't get a perfect triangle, but you can manage the orbits of while you're in the L4 and the L5 in a way that you actually stay within a very tight region across the entire thing. So, look into the giant 200 million kilometer equilateral triangle as a possibility as well. Does like, where is that trade-off, do you think? You were talking, say, 10 million miles, so whatever, 15 million kilometers, a few ahead, a few behind. Is it more about the aperture of your telescope, or is it more about getting that big baseline, or both?
Well, I'm going to answer that carefully, because there's going to be impossibility limits of those 3 levers. Some of them going past a certain point is going to probably make the thing unengineerable. I don't know where those lines are. What I do know is that 300 meters squared each, and dish antenna, a light bucket antenna, and 10 million miles is at least near the realm of possibility that we can engineer. I imagine that the necessary size of the antenna and the distance are a trade-off with each other. And there's also a trade-off of the time precision that you need. And one of those variables is going to be the impossible point. And it may well be that maintaining a distance of 1 meter or whatever it is over 100 million miles is the thing that's so impossible that it's not even worth that's the limiting factor for the architecture is what I'm saying.
Yeah. And this is, of course, these are the kinds of questions that you are, I'm sure, asking yourself as you're approaching the actual design process of this is running the math on all these. And
something that's less obvious, and I know that because I got rejected once for not having enough science on the project, but all of this has to be in service of scientific measurements that can meaningfully do something. So I've seen, and there may well be a point where we could even build it, but it would not add meaningfully to the science capability of the mission. So that's not the place to put the gold, basically, and to put the risk. You're always juggling kind of cost and risk. And by definition, these are all risky, but we're not up to the point of, a NIAC study is not really up to the point of considering risk other than what's actually possible or not, right? Later you figure out, okay, you have a risk list for the mission, but that's many steps ahead.
Yeah, that's when you graduate from phase 3.
Yeah, something like that, yeah.
Yeah. So then, does this tie you down to one target?
No. I suggested TON 618 to the team because I find it utterly fascinating, but the scientist on the team, Slava Turyshev at JPL, came up with a bunch of other targets, some of which I hadn't even heard of. But my goal was really starting with what's the most ridiculous target?
Yeah. What's
the most extreme and ambitious one? And I knew generally that if you start there, you're going to find stuff closer. You know, I didn't know what it was, but I knew you would. And when you're proposing a NIAC project, you need a big major science outcome, but it helps to show, oh, it can do this and that and this and that. It'll push things forward in this way and that way. Yeah, lots of targets. I just happen to like the big ugly one.
Yeah. Well, and for those of you out there who are listening to this and that name Slava Turyshev seems familiar, he's of course the mind behind the solar gravitational lens. So he is a graduate of the NIAC program, got all the way through phase 3 with the solar gravitational lens and has worked on many projects. I've interviewed him many times. He's an absolute treasure. So
I agree. Yeah.
So that's great. So you've got this tool and that there are other, like, obviously it would also perhaps be useful for the third largest black hole of its like size in the, its actual apparent size in the sky, that this same technique is going to work for whatever you want, or you can point it at M87 or at Sag A star as well, right? Like you're going to get size information. So then is there something really specific and important? Because like with the Event Horizon Telescope, that gets us to the shadow of the event horizon cast by the black hole. Follow-on observations have given us the magnetic field lines around these black holes. What does a, 15 million kilometer baseline interferometer with 300 square meter radio or telescopes get us in sort of in the vicinity of the black hole? What are we looking at? The photon sphere or what?
Yeah, we're looking at the photon ring. That's at least the primary scientific target as of now. And the photon ring refers to when you imagine a black hole or see it in film. It's the glowy, twisty region around the jet black event horizon, and it's what it actually is the light that hasn't yet fallen into the black hole. And my understanding from Slava's very patient explanation is that particular property of that black hole and many others is a big unknown in a lot of the cosmological models of the universe that we have. And that constraining that measurement could actually really make a real impact on triaging these models and figuring out which ones are like which of these models does the actual evidence support what we have incompletely. And that, I think, is why he agreed to join me on this quest. And there's other things that can be done, like basically something like this would allow us to create a more broad, standardized scale of black holes themselves in the same way we have those for stars, and that would contribute to the cosmological work that's going on.
Yeah, the Hertzsprung-Russell
Yes,
diagram.
yes.
Yeah. Right. Okay. So what other applications do you think this would have? I mean, you're going like, hey, let's take a picture of the biggest black hole in the entire universe that we know of. That is impressive. But what do you think this ability to detect minute changes in brightness would be if this was a more Swiss Army knife of a tool for people?
Well, what interested me so much about the Hanbury-Brown and twist effect was that it is resilient to a lot of the things that get in the way of other measurements. So it's another eye on the universe that, well, I think we always need more of, kind of like how gravitational wave measurements are its own eye on the universe. And until a couple hundred years ago, we didn't even know about the non-visible wavelengths. And once we started looking there, so it's a way of seeing things farther and smaller, measuring physical properties of regions in space that are so far unmeasurable any other way.
Right. So essentially you are determining intrinsic qualities of this, of any object purely by the variations in the light that is coming from it. And it gives you another tool in the toolkit for astronomers to use. I mean, you think about how measuring brightness has gotten to this revolution in exoplanets, right? And you think, well, would that work?
Well, I actually am curious about that, whether something like this could perhaps be applied to finding smaller and smaller exoplanets around either bigger and bigger stars where the signal is even more. But actually, one of the other NIAC fellows who I hope you reach, he has this amazing idea of another kind of VLBI instrument to actually visible light image continents on exoplanets, basically by separating the starlight from the planet light, for lack of a better word, with an interesting approach. But we're getting closer to a Star Trek present or future when we can actually see the ground on other planets around other stars, which I didn't think I'd live to see. And again, part of the phase 1 study is figuring out applications like this. We have the main goal that got us the study, and that has the bonanza of cosmology. But when you have a tool, what is it? When you have a hammer, everything looks like a nail. To create a new kind of tool, or maybe modernize a kind of tool that will have perhaps a narrow range of applications where it's most suited, is still a new tool. So, there's the technologies involved to actually execute it will have applications elsewhere, particularly the metrology of measuring how far apart these things are and holding them, station keeping, and the electronics too. So I hope to be able to write at the report many pages about here's how else you could use this. Here's the other problems this could solve. That was some of the most fun of my last NIAC projects is, we accidentally invented this, but hey, here's a pathway to solve problems X, Y, and Z that maybe we didn't know about. And I think that's what NASA is really well suited for is set a really ambitious distant target and see what falls out. Kind of like how Apollo led to all kinds of medical technology and materials technology and stuff like that sadly, and people don't talk about anymore, but is still there.
Yeah, I mean, there are a lot of ideas that were originally proposed as NIAC grants and went through the process and then have been absorbed into other concepts. You look at the Habitable Worlds Observatory, the star shade that was going to be going with that spacecraft has now been, came directly from the concepts that were proposed 20 years ago as a NIAC grant. And now it is mainstream. Probably, people are considering whether it's going to be in orbit around the Earth or whether it's going to be launched with HWO, but that we could see this technology get us those first glimpses of exoplanets.
There's a study from 1960 or 1961, and it basically is the first time the Apollo architecture was laid out mathematically, as in one giant rocket. And if I didn't tell you, you'd read it and it would read like a NIAC report. And I was trying to get the program office to let me give a talk where that would basically be the punchline, but I haven't succeeded there yet. But I think it is so strikingly NIAC that I want everyone to read it. It reads just like, yeah, we know this looks impossible, but actually it might be.
From first principles, it seems to work. Yeah. It is amazing to me how many of the great ideas that are just being implemented today are in these papers back in the 1960s. You look at fully reusable two-stage rockets. You look at closed cycle environmental systems, water reuse. You look at, it's just crazy. It's crazy. They were figuring out artificial magnetospheres and inflatable habitats for the moon and human flybys of Venus. And it's all in there that the sort of the place where science fiction and reality cross was between 1961 and 1969. Amazing.
Well, in 1972, NASA was fully expecting to be assigned to send the Saturn V to Mars. And they had studies that it was figured out. They thought they could do it by the 80s. But there's one more old report, even older, that I want to say it's from the late 40s. And I want to say that Arthur C. Clarke was involved in it. It imagined Earth orbiting satellites that had a crew to operate the cameras. And what I love about that so much is it was imagined in a time when the satellite technology was practical and was incoming. But the computer technology was so far away, they thought they'd have to put a guy up there to push a button. And that was such a short window. It's really an amazing relic of a snapshot of a very particular time when the space technology was outpacing the computers.
Yeah, absolutely incredible. So I'd like to talk a bit about your company. Sure. And so, this NIAC proposal comes from Orbital Velocity. And so what is the company?
Sure. So it is a small aerospace engineering and business development company, in short, but I would like to think it does something really unique. I have been a consultant for space proposals for many years, but this is the first time I have a team. And I have what I believe is a very special team, which is mostly made up of people who got laid off from NASA last year. And when that happened, I was pretty upset. I wrote an article that's still on NASA Watch, comparing it to when the Chinese 500 years ago got to the Mediterranean and said, nah, and they went back and burned all their ships. I compared it to that. I still think that's accurate characterization. But so I decided that I was going to not just do the work, but find more work than I can do and find people to do it. And so, and my theory was that, well, a lot of these people are getting laid off from the left hand of NASA, but the right hand of NASA still needs them. And I knew this personally. And it turned out to be, and not just NASA itself, but all the organizations that performed for NASA, universities and labs and things. And that turned out to be a fairly accurate statement. And so far we've had a couple of big projects and a couple of small ones. We got a NASA mission through System Requirements Review, basically filling in the gaps of their team, partially that were happening due to the federal government changes last year and the follow-on effect that had on universities. A lot of universities were very hesitant to hire because the federal government was perceived as there was a lack of stability. But the missions still have to happen. And that was my thought a year and a half ago at this point. And so it was very gratifying to be able to get people that I knew, that incredible people, either laid off or forced to retire. There's the word voluntold. I can't quite phrase the retirement version of that, retire told, but for example, one of the operations expert for this mission that I placed implies it's like a headhunting thing. It's not really. It's much more hands-on. But he had been at JPL for 50 years and was a project manager back to Voyager. So what better person for a emerging mission with a so basically that's what Orbital Velocity does, and we do it for missions and technology development and proposals and and it's very gratifying for me because I get to learn all kinds of stuff every day, learn from lots of different organizations and companies. And obviously I like to talk. So the fact that my role is half communicating than talking, is fine with me. And I've got an endless amount of talent to put to work, and it's very rewarding to do so because I believe very strongly in the critical nature of keeping our workforce motivated, busy, and contributing to American space leadership.
It's interesting to me. Like, I was watching this whole thing and reporting each stage of it, and originally the layoffs were going to be pretty severe. You were looking at cuts to a quarter of the workforce more, and big budget cuts as well that were going to go hand in hand with that. And then the House was able to stop those budget cuts, but I think a lot of the layoffs had already carried through. And so you've got all of these people who, as you said, early retirement, people who didn't want to retire, but could just see this increasingly uncomfortable environment to try to continue their day-to-day work of working on space missions or whatever. And the people who did get legitimately laid off from whichever working groups they're in. And it was very much like, we're going to pull these 3 people out of this, it's a tight-knit team of 10 people and 3 are gone. And this institutional knowledge, we got people who have been around, as you say, for 50 years, who were there for, who learned all the lessons the hard way about how all these missions kind of work. And so you put that on one side, and then on the other side, you look at the just dramatic progress that's happening from the Chinese, the sort of resurgence of the European Space Agency, how the Indians are doing an incredible amount of work. You've got folks in the Middle East and many other countries are building their own space agencies. The Koreans are launching rockets. The Japanese are going to Phobos. Like, there is huge demand for engineers around the world. And like, what is the biggest company that just went public? SpaceX. Yeah. And they're hiring, and then they're in incredible competition with Blue Origin. And then you've also got, right? And so, like, on the one hand, the heart of the institutional knowledge of space exploration was severed from NASA. And then on the other hand, you've got just the absolute rapacious demand of all of these people by all of these different groups. And you're going,
yeah, basically.
Right? Yeah. Like, maybe we can just take the people who need engineers over at SpaceX or in Korea, and let's just find them some jobs, because they were retired.
Exactly. And I would love to find a way to do it internationally. That's a bit harder. But yes, that's the vision, basically, is maybe one of the biggest ways I can have an impact now is connecting those dots. And I think that 10 years ago, I wasn't ready to do that. But now I'm sufficiently motivated to work, to focus on that. And what I think is maybe less obvious than other things is that these people are not fungible. You can't just fire people and then hire people and then expect these first of their kind, never happened before, trailblazing things to work. And further, there is an enormous follow-on morale impact on junior people and young people and students. And when they all have many more commercial opportunities to go to, which is great, I'm not dismissing that at all, it makes it even harder for NASA to have the people available to do the longer term things. Now this what is it? This sort of like there's some major hiring challenge that NASA has announced, or the core, some kind of 2-year rotation in and out that I've seen. Maybe that will help, but you already had those people. You can't treat NASA like a private equity acquisition that you lay off people and then expect to be able to hire a straggler or hire a 10% back and get it working.
Yeah, and especially when there are these other opportunities, these other nations where people can work at, and all of this demand from the commercial side, and just the experience, the lived experience of feeling in this uncertain place where your work isn't appreciated and you don't know if you're going to be on the chopping block tomorrow. Really, Only if you're truly desperate are you going to take that kind of a job.
Yeah.
You're going to look for the one that gives you the safety, the security, they actually want me around here feeling, the vibes, right?
It's a management approach that assumes that people only do their job out of fear.
Yeah.
And that is not the case for the vast majority of people who work for NASA or the NASA centers.
I know many of the people who are watching this, listening to this, were part of those groups that were laid off or took the early retirement, but they still they have some fuel in the tank. What's the best way to connect with you?
I mean, LinkedIn. My name is going to be spelled properly on some text form of this podcast.
Oh, I promise. Yeah, there's no way we'll get that wrong.
Sure. I just mean, look that up. I'm the only Jeff Nosanov out there so far.
Yeah. And Orbital Velocity LLC. I did a Google search for it and you show up.
Okay, it's orbitalvelocity.space, not .com. But get through to me there. I can't remember the last time I was away from my email for more than an hour when I wasn't asleep.
I've experienced this personally.
Yes. So I do, and I always want to hear from people. And I'm actively working on trying to find ways to get people back to work or to work for the first time, people who are passionate. And I would love to help if I can. And anyone who's listening who is part of one of these large organizations that could use some staff like this, let me know. I can find basically any skill set.
How about building orbital data centers? I hear that's going to be big.
Yeah. Well, an orbital data center is basically a spacecraft that generates 1,000 times the heat of most. So it's got all the same problems as every spacecraft and more.
Yeah, perfect. Need some experts for that.
Yes.
All right, Jeff, here's the question. What are you obsessed with right now?
Well, I'm obsessed with thinking of even bigger experiments than OBLIVION with even larger science impact and proposing them to a future NIAC round.
Can you give us a hint? Have you got an idea, or are you still looking around?
I will say that there are several major commercial, global, national security related areas of science that are critical that we understand better. One of them being space weather. And I've got an idea for something kind of orthogonal to all the current systems that might be able to shed some light there. That's the practical one. Practical, but still extremely challenging.
Like predicting space weather.
Yes. Well, and I'm certainly, there are many organizations that have that on the top of their list, particularly because of our total and utter dependence on not getting blasted by the sun.
And the inevitability of us getting blasted by the sun and the horrible damage that will occur from us getting blasted by the sun.
We'd have to go outside and talk to each other in the same, in the same space. We would have to go to a store instead of Amazon. But of course, then the major global economic impacts of that.
Yeah.
And the other thing I'm interested in, the other thing I'm interested in is there's this phenomenon called frame dragging, where basically a large massive object pulls space-time around it as it rotates, like the Earth even is large enough, and the sun certainly. And it was just measured around the Earth. It was just proven to be a physical thing that happens. And I find that really interesting because, well, wouldn't it be great if we could manipulate space-time? FaceTime works pretty well. Space-time, in some way, that would be a pretty major change, kind of along the lines of manipulating chemistry and, a couple hundred years ago, manipulating radio 100 years ago, and manipulating the atom 75 years ago. So if such a thing were to be possible, or I should say engineerable, that would have very large implications on everything from space travel to power, who knows. So when my mind wanders over there, I let it stay there for a while, and I end up with a list of articles to read and Wikipedia things to read. But
really careful that you don't bring up this idea with ChatGPT, because it is going to 100% let you know that you've come up with an absolute breakthrough and drag you into AI psychosis.
I'm glad you mentioned that, because being able to bounce ideas off of an AI that's trained on all of human knowledge is a really weird place to be. and is extremely powerful. It's worth its own separate conversation, but I have been goofing around with the AI systems, and they're great for revealing sources you didn't know you should look for, and so it's fascinating to be in this world now when these tools are trivially available. It'll be very interesting to see where they go in the next 5 years, and obviously indefinitely.
Yeah. And I mean, they're getting better every day, but the danger is that they're too eager to please and not eager enough to tell you why your thinking has a absolute flaw, that if they just pointed it out to you in sort of equation number one, then you wouldn't have spent the last 5 days in a AI psychosis stupor, ignoring your friends and family to chase this rabbit all the way down the hole to lead you nowhere. So yeah, that is the danger and the risk. On the one hand, someone to bounce your ideas off. On the other hand, someone to destroy your life.
Right. And I think that my kids are in middle school and one's middle and high school. And the temptation to outsource your thinking to it entirely is a really interesting question. And I constantly wonder, if you go back to the first movable type press, all the way up to the calculator, the graphic calculator, are these things all on one line, or are they different? I guess you could say I'm kind of obsessed with that. And where does AI sit on that? Is it just the next logical thing 800 years down the line from the printing press? Or is it a fundamentally different thing that changes how we think, and in a way that we should resist? I don't know yet.
Yeah, no, I mean, we were supposed to do this interview yesterday, and I canceled with you because I had a plumbing problem, and and usually that's nasty. Like, you don't want to tell a person what your plumbing problem is. But in this case, I don't mind, which was that my irrigation system failed, my drip irrigation system for my garden, and I had to diagnose the problem. And a year ago, I would have called the plumber. Right, because I didn't know where it was wrong. But now I was just like taking pictures of various devices on my plumbing system.
Yeah, is it this? Is it that?
Is it this? Is it that? Okay, let's try and segment the irrigation system down. And it was one filter that was in a box, hidden away, that hadn't gotten a regular cleaning. And I brought it out and gave it a cleaning in bleach, and then suddenly, boom, the system is working again. And so, was I offloading my cognitive load? Probably. Yeah, I probably could have figured this out if I just kept unscrewing things and taking things apart and got to the bottom of it. But I would have just called a plumber, and that's offsetting my cognitive load as well. Yeah. But when you're seeing these kids these days who are just taking the question coming from the teacher, and then they're plugging it into ChatGPT and then giving them the answer. Yeah. That is the other side of the spectrum that you absolutely don't want to do. So.
Right. And what lies in that spectrum between that and, my refrigerator is not making a weird noise, recording it and sending it off to ChatGPT. And that's an interesting space.
Yeah, totally. Yeah. It's there's a quote, this guy named Z. Moskowitz has this great quote, which is that AI is if you want to learn something, no better tool has ever been invented. And if you want to not learn something, no better tool has ever been invented.
Oh, I like that. Yeah.
And you can sort of live in that world between both of those. Well, Jeff, we've reached the end of our episode. I want to thank you so much for taking the time to chat. Good luck.
Likewise.
With your NIAC award. Definitely, when you meet the other people, just remind them that email that they got from Fraser is legitimate, and that they'll have a good time talking with me. And our audience is hungry to hear what their ideas are, and they can't wait to see them go to the next stage. So good luck getting to phase 2.
Thank you, and thanks for having me.
All right, take care. I hope you enjoyed this conversation with Jeff Nosanov. Now, I had a longer conversation with Jeff, as I am like to do, and we talked about his podcast, where he has been interviewing researchers at NASA and other space agencies. And if you look through the list of the people that he has interviewed, it's pretty amazing. And we just talked about what it's like to talk to some of these people, some of the cool stories that he's done, and where he sees things going in the future. So if you want to hear that longer version of this exact same interview review. It's over on Patreon. It's completely for free. You don't have to subscribe. Just click the link down in the show notes and go over there and watch it right now. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailock, Dark Finga, David Gilton, and David Matz, Enthralla Reading and Math for Toddlers, Evan.Pro, James Clark, Jeremy Madden, Jim Burke, Marcel Smith, Michael Purcell, NASA Ocean Guy, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Rinkaidu, Richard Williams, Sean Sargent, Stephen Filer Munley, Team 49, Tillsubs Canada, Vlad Chiplin, Wolfgang Klotz, Zelda, it sounded funnier in my head, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. All right, I've got to say, I'm very excited to get back into the NASA NIAC Award season. By the time you're watching this, I've probably interviewed 3 or 4 people. There was about 20 this time around, and I sent out emails to every single one of them, and I'm just going to be hooked into them like dog with a bone, trying to make sure that I can get each person to do an interview with me, and I'll bring them all to you as soon as we can. So you will probably see NIAC season unfold over the next couple of months, but I hope you enjoy this as much as I do. If you haven't seen these before, we have show notes for all of the previous NASA NIAC Award seasons, so you can just go back and check all of them out, and I think you'll find all these ideas really interesting. All right, we'll see you next time.